Awesome. Okay, thank you. So, yeah, so I just want to mention this is joint work with Rob Davis, who's at Colgate University, Morgan Lane, who's at Martha Lane's Collins High School here in Kentucky, and Liam Solis, who's at KTH. Rob and Liam are my former PhD students, and Morgan is a former master's student of mine. So let's see, can I make this work? Yeah, all right. So let me try that again. There we go. All right, is that all visible? Johannes, you can still see after?
Yes.
Okay, great. All right. So what I'm going to do is start out with some fundamental definitions and just to make sure we're all on the same page, and then get into the new work. So we're going to start with lattice polytopes. I'm assuming everybody knows about lattice polytopes, but we'll take the convex hull of a collection of integer vectors in d-dimensional space. I'm going to assume that all of my lattice polytopes are full dimensional. I just won't worry about low dimensional objects in a higher dimensional space. This is an example. And the first thing we're going to do is take the cone over P. So we lift all of the vertices of the polytope up to height 1 in RD plus 1, and then we take the non-negative real span of those. And so when we move to this homogeneous picture, then a lot of properties for the polytope become easier to understand. And so the two of the conditions that we're particularly interested in are at the intersection of arithmetic and geometry in this lattice polytope picture. One is that P has the integer decomposition property, or we'll abuse language and just say P is IDP. Sometimes I'll say P has the IDP. Sorry if you're a grammar, fanatic, it's going to bother you. But P is IDP if for every point in the cone at height k, so the 0th coordinate is this height coordinate because I'm appending the height 1 at the beginning. For every point in the cone at height k, there exist k lattice points in P lifted to height 1 such that those lattice points sum up to ky. So another way to think about this is that linearly, we know that the cone is spanned by points at height 1, but this is saying that also arithmetically, we have the lattice points at height 1 in the cone coming from P additively generate all the lattice points in the cone. So that's the first condition we're interested in. And the second is that P is reflexive if the dual of P is also a lattice polytope. And the remark I'll make is that IDP is equivalent to projective normality of the associated toric variety, the toric variety associated to P, and reflexivity implies Gorenstein-Fano for that variety. By the way, correct me if I do any of these dictionary translations wrong. I'm not an algebraic geometer. I'm really a combinatorialist, and so my motivation for these things comes from the combinatorics and the polyhedral geometry side, but I know that these are of interest also to geometers. So pretty much, if you're primarily interested in the algebraic geometry, just replace the words every time I say IDP or reflexive. All right, so just some basic examples. If you haven't seen these, are lattice cross polytopes. These are the convex hull of all the standard basis vectors and their negatives. If you take the dual polytope to those, you get the -1, cube. And I think I didn't say P is reflexive if the dual of P is also a lattice polytope. So these are the two conditions I'm interested in. And these are just standard examples. So there are some general challenges regarding lattice polytopes. These are all quite difficult tasks. The first would be identifying when a lattice polytope is IDP. So when this arithmetic generation of the cone is coming from height 1. A second is classifying reflexive polytopes of fixed dimension. We know that in each dimension there's only finitely many reflexive polytopes up to unimodular equivalence. A third is classifying all lattice polytopes of fixed dimension and bounded volume. And a fourth task that's difficult are determining different algebraic invariants like the Ehrhart series or the Poincare series associated to the cone over P. And really what's happening, I'll talk about this later, is that associated to the cone, you've got a semigroup algebra The Ehrhart series is the Hilbert series of that semigroup algebra, and I won't talk about it today, but you can also study the Poincare series of that object, or of, yeah, I'll leave it there. And so one comment I'll make, where I'm coming from is that there's a range of interesting conjectures about all lattice polytopes, or at least very large classes of lattice polytopes, that are motivated by behavior of well-behaved families of combinatorially defined polytopes. So, you look at zonotopes, lattice parallel pipeds, you look at symmetric edge polytopes or edge polytopes, polytopes coming from simplicial complexes, permutahedra, all sorts of things that we see this really nice behavior with, that then people start asking, is that true for some much bigger class of lattice polytopes that leaves the combinatorics behind? So, pardon me. So the main questions that we're motivated by are about the intersection of IDP, reflexive, and Erhard Hstar vectors, which I'll define later in the talk. And so one question by Hebe that was back in the 90s is, do all reflexive polytopes have unimodal Erhard Hstar vectors? And the answer to this is no. Maybe 14 or 15 years ago, counterexamples are found by Payne and Mustada. But these two questions, the second and third question, are both still very open. They're both special cases of conjectures due to Francesco Brenti that were also asked by others, Hebe and Asugi and Scheppers and van Lanenhoven. The first is, if you have IDP reflexive polytopes, do those all have unimodal Erhard Hstar vectors? And Scheppers and van Lanenhoven dropped the reflexive and just asked, do all IDP lattice polytopes have unimodal Hstar vectors? And so these are questions that fall within a broader set of questions about the interaction of reflexivity, IDP, variampleness, Erhard Hstar vectors, and other topics. But these are problems I've been thinking about for a while. And to be honest with you, I don't really have a good sense of whether the answer is yes or no. It kind of changes every few months, whether I think the answer is yes or no. So for us, our project goals are, this huge family of polytopes seems too big for us to meaningfully really try to tackle at this point. I mean, a lot of people have worked on these problems and had trouble making much headway beyond a few things that are already known. So our goal is to focus on a specific family of lattice simplices that's sufficiently complicated to be interesting, in that they're farther away from the combinatorics. We're not just looking at combinatorially defined lattice polytopes, but where these simplices admit reasonable computational experimentation in high dimensions, and also do admit concrete tools for proving properties like IDP and reflexive. And so in this, the structure of the talk kind of mirrors the structure of how we've been going about this, which is we first want to investigate the reflexive and IDP properties for these simplices, especially their intersection, and then kind of turn our attention to unimodality questions.
Ben?
Yeah.
Just could you quickly remind us what unimodality means?
Oh, yeah. So I'll define that later. But unimodality, if I have a vector, unimodality means that the coefficients weakly increase up to a certain point, and then weakly decrease beyond that. So yeah. So.
Thank you.
Yep. And so there are all sorts. I should say that there's a long history of interest in unimodality problems associated with things like the Hard-Lefschetz theorem and various unimodality conjectures about Kohn-Macaulay and Gorenstein rings and their Hilbert H vectors. So this is connected to a lot of different questions in both toric geometry and combinatorial commutative algebra. Okay. Let me tell you what these simplices are. Again, these might be familiar. So what we do is we take a vector of non-negative integers. I'm typically going to assume that this vector is an integer partition. So you can think of these Qs as either weakly decreasing or weakly increasing, however you prefer the convention. But I take a vector of non-negative integers. I set EI to be the ith standard basis vector in RD. and I take the convex hull of the standard basis vectors with the negative q vector. And so this is a lattice simplex. It has a single unimodular facet coming from the standard basis vectors, and then essentially the arithmetic behavior of the simplex is controlled by the q vector. And so our motivation for studying these particular simplices is that they correspond to certain weighted projective spaces, which are of interest to algebraic geometers and others. These simplices have a Hermite normal form. If you look at the vertices, the matrix for the vertices has a Hermite normal form that's what's called a one-column matrix. Those simplices have been considered previously by Hibi, Higashitani, and Lee in the context of Erhard theory. And in principle, all the properties of delta 1q should be obtainable from number theoretic properties of q. So what we're doing is we're sort of moving away from the combinatorics and instead replacing combinatorial complications with number theoretic complications in the hopes that we might see some interesting behavior that will shed some light on those questions that I mentioned. All right, so for reflexivity, there's a theorem, I don't know whether to cite Conrad's or folklore, so that delta 1q is reflexive if and only if for every j between 1 and d, q sub j divides the quantity 1 plus the sum of the q's. And throughout the talk, I should mention, I'll refer to the q's as the weights. So if you take 1 plus the sum of the weights, each weight should divide that. And I want to emphasize that what that means is that 1 plus the sum of the weights is some multiple of the jth weight for every j. This k is a function of j. It'll vary. And the proof of this follows immediately from the duality definition of reflexivity. Okay. And in fact, this quantity 1 plus the sum of the weights is the normalized volume of the delta 1q simplex. So we denote that by n of q for normalized volume of delta 1q. Okay. So there's a simple arithmetic condition to determine reflexivity based only on number theoretic properties of the q vector. And so just as an example, if I take q equal 2, 2, 5, I take 1 plus sum of the q's, I get 10, which is divisible by both 2 and 5. And this is a picture of the resulting simplex. You've got this one unimodular facet and then this kind of tail point far away. So one thing that we'll be talking about a lot, or that I'll be talking about a lot here, is that when I look at this vector of weights, what I really want to focus on is the distinct entries and their multiplicities. And so what I say is that a vector q or delta 1q are supported by a vector r, and my standard notation here is going to be that r has k entries if there exist positive integers x1 through xk, where q is r1 with multiplicity x1, r2 with multiplicity x2, etc. We also might denote that by the pair r comma x. Okay. So as an example, 2, 2, 5 is 2 with multiplicity 2, 5 with multiplicity 1, also denoted by the support and the multiplicity vector. Okay, so these are the simplices we're interested in. So let's focus a bit on when are these things IDP and reflexive. Okay, so we know a few things already. So for each R vector, so for each set of distinct entries in Q, you can ask what types of reflexive delta 1 Qs are supported on that particular set of distinct weights with some multiplicities. And so with Rob and Liam, I previously proved that there's infinitely many reflexives supported on a given R. And before that, I had proved with Rob that given two weight vectors Q and P, where delta 1Q and delta 1P are both reflexive and IDP, you can create a new vector, P star Q, where delta 1 P star Q is reflexive and IDP. So I can take two of these, I can combine them through this operation and produce a new reflexive IDP polytope. And the operation that the geometric interpretation of P star Q is that it corresponds to what's called an affine free sum of rational polytopes. So what that tells us is that there's infinitely many reflexive IDP delta 1 Qs that arise in this manner. And the thing I want to mention is that when I do this, the support of P star Q is, it includes the support of Q, or sorry, of P, depending on how you define it. It contains the support of one of these, but then that support gets larger. So this does not preserve that support vector, the R vector, okay? And one thing that we'll see soon in the talk is that if you have a fixed R vector, and if one of the distinct weights in that vector divides the last weight. So again, what I'm saying is I've got that Q is R1 multiplicity X1, etc., and the R's are increasing. So what it says is one of these smaller R's does not divide the largest weight, okay? If that is the case, then only finitely many of these infinitely many reflexives supported on R will be IDP. Okay. So when you put the reflexive condition on a distinct set of supports, then that does not push you into a finite setting, but with this, kind of mild restriction, IDP really crushes down the number of delta 1 Qs that are reflexive IDP. And when I say that, what I mean is really there's a very, there seems to be a very small number. So if you consider all of the R vectors that are partitions of n up to 75 with distinct entries, because the entries of the R vector are distinct, and look at only those where we have this non-divisibility condition, there's some entry, there's one of the distinct weights that doesn't divide the largest one. There's around 500,000 R vectors of this type, but there's only 509 IDP reflexives supported on them. And so, if I understand the dictionary correctly, what this means is that if you are looking at the Gorenstein-Fano varieties, there's infinitely many Gorenstein-Fano varieties that you can build out of these delta 1 Qs where they have these R vectors as their distinct weights. But the number of projectively normal ones among that is only 509. And the other thing I want to mention is that even though that's a lot of R vectors, a lot of distinct entries, in reality, our feeling is that this is a very limited glimpse at the data. And just as one example, if you take the Q vector 210, then 4 211s, and then 41 1055s, this is not among that sample, but it is both IDP and reflexive, and 210 doesn't divide 1055. So, so we really do have, in my opinion, we can easily find Q vectors that are outside this sample. And anyway, I mean, it still took a while for this all to get crunched, to get computed. Okay. So we should ask, how do we actually detect this? So we know that the reflexive condition can be tested by a simple arithmetic division condition. The IDP condition is a little more complicated. So if you start with a reflexive simplex delta 1 Q, it is IDP if and only if the following holds. And so I often kind of skip the details of this page, but I want to just talk through it a little bit to give some context of what's going on. So there's a condition that says for every j between 1 and d, so in other words, for every weight, and for all values between 0 and 1 minus the weight that satisfy this inequality, where you have this, nonlinear function be greater than or equal to 2, there has to be some positive integer c less than b that satisfies this set of equations. Okay, and these are just a bunch of nonlinear equations, involving 4 functions. And so where does this come from? Well, if I start out reflexive, then to be IDP, one thing I can do is I know that I have the origin lifted to height 1. So if I just subtract off as many copies as the origin as I can, I'll end up on the boundary of the cone over delta 1q. So I start out in the cone over delta 1q. The origin lifted to height 1 is in that cone. Subtract it off until you end up on the boundary of that cone. You're on one of those faces, the cone over one of the faces of delta 1q, that's this for every j equals 1 through d. I've got to check every face. And what I need to do is I need to show, or every facet, I need to show that every facet of delta 1q is IDP, and that is what this does. I'm saying for every facet, I'm going to check IDP, and that's where I'm getting these. And what's really happening is I'm saying I need some integer point at height 1 in the cone in that facet. This third equation is telling me I'm at height 1. This first equation is telling me I have a point at height more than 2 that's in the fundamental parallel pipette, if you know what that is. Then I need to be able to subtract it off and stay in the cone, and that is what these equations do. So this really is just an arithmetic, a direct arithmetic translation of the geometric, these geometric movements on the lattice points in the cone. Anyway, and I'll say that both for computing and for proving things, you can actually make use of these equations. The proofs are not pretty, but it can be done. So what is really helpful, though, is that you don't need the full strength of this in certain cases. So we call this theorem the necessary condition, and it's very useful. So if Q is reflexive in IDP, then for each j between 1 and d, you have that 1 plus the sum of each weight modulo qj is equal to qj. So remember that if delta 1q is reflexive, then for every qj, I have that the normalized volume, 1 plus sum of the weights, is a multiple of qj. And what this is saying is if I subtract as many qj's as I can out of each weight and add up all the remainders, I actually get qj itself. Right. Now, if you're reflexive, you'll be some multiple of qj here. But to be IDP, you have to actually be equal to qj. It's helpful to reframe this into our notation using supports and multiplicities. If Q equals Rx is reflexive and IDP, then what am I doing? Well, for each distinct weight, I'm reducing it modulo Rj and then adding it up with that much multiplicity, and I should get Rj. Okay, so if I frame it in this way, then I get a corollary. This corollary is where we get the finiteness condition that I mentioned earlier. If I have a Q vector supported by R with multiplicities on the weights x, that is both reflexive and IDP, and if there is some distinct weight where that weight does not divide the largest weight, then the ith multiplicity has to be greater than or equal to 1 and less than or equal to Ri plus 1 divided by Ri. And remember, these R's, I listed them in increasing order. So this is some value, strictly increasing order. So this is some value greater than or equal to 1. So this inequality is legit. And then 1 is also less than or equal to xk, which is less than or equal to Rj divided by Rk mod Rj. And remember also that Rj does not divide Rk, so this is going to be a non-zero value. Okay. So this is what tells you that there's only finitely many multiplicities that are candidates for an IDP reflexive delta 1q supported on this R. Okay. Maybe before I do that, let me just ask, are there any questions? Has anything popped up in the chat? I can't see the chat, so. Or does anybody have any questions at the moment?
So far, nothing popped up.
Cool. Either everyone's enthralled and I'm doing an amazing job, or everybody's on their email, and either way, it's all good. Global pandemic and all. So.
I enjoyed.
Okay. So one thing I want to emphasize here is that so far I've taken distinct weights and I've asked what can their multiplicities look like, right? So if I want to look at these Gorenstein-Fano projectively normal weighted projective spaces, you know, what do the multiplicities on the weights look like? But we can also change perspective and ask what happens when we think of the entries of the weights themselves in terms of the multiplicities. And that turns out, I think, to be really interesting. So for 1 and 2 supported delta 1 Qs, this proposition is straightforward. If you have a weighted projective space with a single distinct weight with multiplicity, if it's IDP reflexive, it has to be the all ones vector. So it's just projector space. Rob and Liam and I had previously proved that for a vector that has 2 distinct weights with multiplicities, then delta 1Q is IDP reflexive if and only if it satisfies the necessary condition. So this condition here, right, that says, you know, I add up the remainders of the weights modulo each possible weight and I get that one, the jth weight. That actually, for the 2 supported case, completely characterizes IDP. And we have a classification of all such vectors. So if I tell you the multiplicity vector, I tell you I want an IDP reflexive delta 1Q where the multiplicities of the weights are x1 and x2. There are only 2 IDP reflexives you can form with those multiplicities. The first is weight 1 and weight 1 plus x1. And the second is weight 1 plus x2 and weight 1 plus x2 times x1. And if you kind of think about what this looks like, well, maybe I'll start up here. If you think about what this looks like, you can see where the structure of these vectors is being driven by the reflexive condition. I need that 1 divides the normalized volume, and I need that 1 plus x1 divides the normalized volume. So if I were to write out the normalized volume, I'd have 1 plus x1 times 1. Well, that's 1 plus x1. Plus x2 times 1 plus x1. I can factor out the 1 plus x1, and I get 1 plus x1 times 1 plus x2. And here I have a similar kind of thing going on. This term, 1 plus x2 times x1, is what you get when you have x1, 1 plus x2s plus the 1. And then you can factor things out. And the factor that you pull out is precisely 1 plus x2, which allows that reflexive divisibility to happen. And in the first case, we have that R1, the first distinct weight, divides the second distinct weight. In the second, it does not, because 1 plus x2, if you divide R2 here by R1, you have remainder 1. Okay. Okay, so sorry about the next theorem. This goes on for 2 pages. So yeah, don't read this too carefully, but let me talk through it a little bit. We can do a similar analysis in the 3 supported case. And so this is what Rob, Liam, Morgan, and I have gotten done. So if you have a 3 supported vector where delta 1Q satisfies the necessity condition. So I'm not going to think about IDP reflexive. I'm just going to think about the necessity condition. And if I fix the set of multiplicities on the weights, then there are only 8 forms that I can have that satisfy this multiplicity condition. And the first 7 of them are particularly important for reasons I'll explain in a minute. Okay? And this looks just horrible, and it is, but you can still see this structure where I have, you know, a 1 plus x1 and then another 1 plus x1. So I'm factoring things out, and I've got, you know, these various things going on. I also want to emphasize that this one in the first set of distinct entries, or the first support, has multiplicity x1. This 1 plus x1 has multiplicity x2, and this quantity here has multiplicity x3, and that's true for all of them. And what is interesting is you tell me the multiplicity you want on the weights, and I tell you, if you want to satisfy the necessity condition, it's got to be one of these. I'll also say, I'll get to this theorem in a minute, but all of these appear to be IDP. We've proved it for some of them. We got interrupted in finishing that by pandemic stuff. But I'll say I'm quite confident that all 7 of these correspond to IDP reflexive simplices. The 8th one looks different, right? These previous ones say, you give me the multiplicity, I give you a vector. The 8th one says, there might be some K and S where if you set the distinct entries equal to this thing and set the multiplicity equal to this, then it works out. Okay, it has a different flavor to it. Every one of these that we've computed so far has been non-IDP. And I'm pretty sure, again, that these first 7 classify the reflexive IDPs that are 3 supported, and the 8 are ones that satisfy the necessity condition, but do not satisfy the full IDP. And in analogy with this idea that when I'm 2 supported, the divisibility relations between the distinct entries kind of control the structure of what you can see given a set of multiplicities. The first 7 of these correspond to all possible valid divisibility criteria among the distinct weights. So if I tell you I want a reflexive IDP delta 1q with multiplicity vector x1 through x3, where the first distinct weight does not divide the second one, it does divide the third one, and the second divides the third one, it's going to have to be this. This 8th one, the divisibility pattern is a duplicate of divisibility pattern 5. Okay. So we are certain that divisibility patterns 1 through 4, these 1 through 4, we have proved that these are reflexive IDP. 5, 6, and 7, we've still got to finish. And 8, we just need to prove that that's not IDP, but all the computational evidence supports it. Okay. All right. And so there's some obvious, conjectures that one can make about, well, if you have, a K-supported vector, with R1 through Rk, and I give you a multiplicity vector, is there some list like this of supports that satisfy the necessity condition, some of which give you these unique IDPs, and the rest of which are these spurious non-IDPs? I don't know if that's true or not, but I would like to know the answer to that. It's not clear to me how to prove a statement like that, because this theorem right here is very much a like, do the algebra, use this necessity condition carefully to get these. Okay. All right. So let me talk a little bit now that we know what we're looking at in terms of IDP reflexives, at least with small support. Let's talk about unimodality. And maybe I should say one other thing first. Even though these have small support, they're arbitrarily high dimension, right? So the dimension of these polytopes is the sum of the multiplicities. And so there's this distinction between being complicated from a dimensional perspective and being complicated from the perspective of the arithmetic. And what this is saying, what we're saying is that the dimension is much less important in these cases than the arithmetic of the weights. All right. So let me tell you just briefly about Erhard theory. So if I take the integer points in the cone over P, okay, and I grade those points by the height coordinate, that 0th coordinate that I lifted it up to, I can form the semigroup algebra for that semigroup, C adjoin P. And then if I look at the Hilbert series, which is also called the Ehrhart series of P, it is precisely the Hilbert series for that semigroup algebra. Now, another interpretation of that is that it's the generating function. This was Ehrhart's context. It's the generating function for the number of integer points in the teeth dilate of P. So it turns out that the height t slice of this cone is a copy of t times p, the t dilated p. And by, either by some discrete geometry or by the theory of Cohen-Macaulay rings, however you prefer to go about it, this has a rational form, and the numerator is a polynomial of degree less than or equal to d that has non-negative integer coefficients. And we call this numerator the H star polynomial of p. We call the coefficient vector the H star vector of p. So if you're familiar with Cohen-Macaulay algebras, you can just think, okay, here's some affine semigroup algebra, and the H star vector is the H vector for the Hilbert series of that. And if you are coming from the Erhard theory side, then it's the Erhard H star polynomial. So there's a theorem due to Hebe that P is reflexive if and only if this H star polynomial has full degree, equal dimension of P, and it's symmetric. You can also get this from a theorem of Stanley's about Gorenstein semigroup algebras. And we say that P is H star unimodal if the H star vector of P is unimodal. So again, that means that in this polynomial, the coefficients they're always going to start at 1, they rise, and then they fall. So in my opinion, the kind of deepest known result about the relationship between reflexive IDP and unimodal is this result due to Bruns and Romer, that if P is Gorenstein and admits a regular unimodular triangulation, then P is H star unimodal. And so reflexive polytopes are Gorenstein. So if P is reflexive, it satisfies Gorenstein. And regular unimodular triangulations imply the IDP condition. So this reflexive IDP fits within this context. And what they actually prove is that if P is Gorenstein then, and admits a regular unimodular triangulation, then the H star polynomial of P actually is the H star polynomial for some reflexive. So if you're thinking about these unimodality questions, it's sufficient to just think about reflexives. And so just a couple of asides, which is things I think, one thing I think is really interesting is the reflexive polytopes that are IDP reflexive but don't admit a regular unimodular triangulation are completely mysterious, both in general and for the delta 1 Qs. These should exist due to some unpublished results by Christian Hasse and one of his students and a previous result of Hasse and Melnikov. So they should exist, but I don't really know that anybody has written down an example, and it's not really clear what this gap is between the Bruns-Romer result and the full reflexive IDP class. And a second comment is, with that in mind, with one of my PhD students, Derek Hanley, we're investigating regular unimodular triangulation starting in this 2-supported IDP reflexive delta 1Q case, and I was hoping that maybe I'd have some results to mention, but it's not quite done yet. Not enough to be able to mention. So what I had said earlier was that if I have the delta 1 Qs, all of these invariants for delta 1 Qs should be expressible in terms of the Q vector. So, here I have an arbitrary lattice polytope, and I've got this H star polynomial. And now the question is, if I have a delta 1 Q, how do I get rid of all the geometry and just write down the arithmetic? And so here's what it is. The H star polynomial is given by the sum from b equals 0 to the sum of the weights of z2, and now I have w of b, where w is some statistic for each of these parameters b. And what you do is you take b and you subtract off the sum of these floor functions, right? For each weight, I take qi times b, and I divide it by the normalized volume, and I floor that. Take b, divide that out. Okay. And so this is coming from a particular parametrization, a particular one-dimensional parametrization of the lattice points in the fundamental parallelepiped. Okay. So what does this look like? Let me just say a couple examples. If Q is the vector 3, 20, 24, 24, 24, 24. So the distinct entries are these with multiplicities 1, 1, 4. The H star polynomial for this is 1, 16, 29, 28, 29, 16, 1. So it just barely violates unimodality because it goes up, dips a little, and then goes back down. And the Hilbert basis, if you know what that is, for the cone, it only has one element outside of the lattice points at height 1, and it's at height 2. And there's actually an infinite family of lattice polytopes that we have looked at. I think it's actually coming from the second example. Yeah. That are very close to unimodal and very close to IDP, like right on the boundary. And we've been trying to see if we can come up with some counterexample to these conjectures by tweaking these sorts of things. And so far we haven't had luck, but we've gotten really close. Anyway, but what I want to say is it's really helpful sometimes to think about how these weights move along. So I think about it as this. I start with b equals 0, and I get that w of b is equal to 0. So I get the constant term 1. When b is equal to 1, I get 1 minus whatever this is. Well, that's actually going to be a 1, so I get a z. So first I get a 1, then a z, and I'm going to keep going up 1, z squared, z cubed, until the first of these floor functions kicks in, and there might be multiple q's that are equal to each other, because this is written, without distinct entries. And so suddenly I'll get up to that b, and then I have to pull back, and I keep stacking, right? And so you can actually visualize this. Let's look at the case 3, 20, 24, 24, 24. And I'm probably going to need to share a different screen, maybe. Let me see if I can. Can I? It's not gonna. Okay, can you guys see that?
That's it. Yeah.
Okay, great. All right, so I just want to say that I told you that this vector looked like 1, 16, 29, 28, 29, 16, 1. Okay. And so the question is, as I go through the parameterization, how does it actually move through? And what you can see is that it goes out a fair ways as it's building the vector up, right? It's layering out all the way up to almost the top degree, and it's bringing all those coefficients up, roughly in tandem with each other. And so as this parameterization is making its way through, all the coefficients of the H star vector are being lifted, kind of in parallel, right? But if I instead look at the vector 1, 12, 40, and 60 with this other multiplicity, let's see, is this visible?
Yep.
Okay. Then what you see is actually a different pattern where it lifts up all of the low degree terms before it moves on to any higher degree terms. So depending on the structure of the Q vector, the way that this particular choice of parameterization that we're using, the way it builds up the H star vector has, it moves differently. And so that makes it a little bit tough to have fully, a fully uniform understanding of how this works. Okay. So.
I mean, do you also observe different behaviors? I mean, these are
Yeah.
just 2, but I guess everything else can also happen.
Yeah, I mean, yeah, I'm a little embarrassed to say how many things I've just kind of been like, what does this look like? What does that look like? And yeah, you can get all sorts of really wild things happening. Okay. We haven't tried to actually quantify that, but the main thing I want to point out is that in these situations where we have examples that are really close to the boundary of the conjecture, almost unimodal. Again, this case is similar, 1, 7, 15, 14, 16, 14, 16, 14, 15, 7, 1. Almost unimodal, almost IDP, but not quite. You can see sort of different behaviors of how our particular description of the H star polynomial runs. So, so that adds some complication to what we can do. And then there's just a naive question that we can ask, which is if you ignore IDP and reflexive, etc., ignore all these conditions, just do we expect the delta 1 Qs to be unimodal at all? And so we ran some experiments. We partitioned these by the normalized volume. And we did compute the H-star polynomials for all 61.5 million delta 1 Qs where the normalized volume went up to 75. But using that as comparison, we actually randomly sampled Q vectors up to normalized vector 100, normalized volume 120 to produce the following plot. And so what this is showing you is if I just look at all the weighted projective spaces, ignore projective normality, Gorenstein-Fano, whatever. I just look at all these delta 1 Qs. If the normalized volume is 20, so if 1 plus sum of the weights is 20, you've got around 75% of the H-star polynomials are unimodal. If the normalized volume is 40, it's around 50%. Again, these are approximate values, but we have exact values for these, and it's pretty close to this plot. And as you move up in normalized volume, you see that most of the delta 1 Qs do not have a unimodal H-star polynomial. And so one question is, where is this going? You know, is this trending towards 0? Is this trending toward some small but fixed proportion? We don't know the answer to that either. I think that's a really interesting question from an Erhard theory perspective. But it also tells you that when we are claiming that IDP reflexives might be unimodal, among the delta 1 Qs, we're claiming that it seems something unusual happens. So I can at least tell you what happens to the H-star unimodality with small support. I know I'm running short on time, so I'm going to kind of just zip through this. If delta 1 Q is 2 supported and IDP reflexive, we know it's unimodal. If it's 3 supported and IDP reflexive, then, as I said, for the first 4 of those division criteria corresponding to those first 4 of the x's of the R vectors made up with the x's on our list, we know it's H-star unimodal. We have lots of computational evidence that for the other IDP reflexives that are 3 supported, also it holds. Unfortunately, one of the things that kind of slowed us down, in addition to just, you know, having other needs due to the pandemic, the proofs of unimodality are not particularly enlightening. Like, you know, it's not clear why it is that the IDP reflexive is what's driving this. It's more just like, here's the vector, here's the multiplicities. Is it, or is it not unimodal? And then we go and run this formula and we do some algebraic manipulations and it is. So that's one disappointing thing for me, is I was hoping that maybe we would get some more insight. So the final thing I'll say, can I take another couple of minutes? Is that cool? I know you said going an hour. Okay. So I mentioned that thinking about the multiplicities is really useful. So we did ask, you know, what happens if we have a reflexive delta 1Q, just reflexive, dropping IDP, with a very large multiplicity for one of its weights? And we just started out by saying, what if the weight 1 has a very large multiplicity? Okay. And we actually, you know, realized, well, we can take any vector at all, take any vector of weights, whether or not it corresponds to a reflexive delta 1Q, we can make it reflexive by just appending enough ones that the division criteria holds. 1 will divide anything. So you take 1 plus the sum of these Qs. If the Qs don't divide correctly, just keep tacking on 1s until you hit a multiple of the LCM. Okay, so do that with the smallest number of 1s you need to prepend, and we call that the first reflexive stabilization. If Q is already reflexive, don't prepend any 1s. Okay. And we call that the number of 1s that you have to tack on, we call that the reflexive stabilization number. So we can write the reflexive stabilization of Q is however many 1s you need in order to make the division criteria work out here. Okay. And you can actually keep tacking on 1s, just keep throwing on LCM of Q many 1s, and that'll keep working. So that'll give us these higher reflexive stabilizations. So the mth reflexive stabilization is defined as take Q, throw in as many ones as you need to make it reflexive, and then throw on as many more ones in blocks of LCM Q many. Do that process m times. So for example, if you take 2, 2, 3, 1 plus 2 plus 2 plus 3 is 8. So you got to throw on 4 ones to make it reflexive. The reflexive stabilization number is 4. If you want to look at the third reflexive stabilization, then you have to have 16 ones because you put in, 12 more ones. And one thing that's interesting is that, unsurprisingly, if m is greater than or equal to 2, you lose IDP. So you really quickly lose IDP when the multiplicity gets too big. But what we find particularly interesting is that if m is sufficiently large, then this is not H-star unimodal. The reflexive stabilization, the mth reflexive stabilization is not H-star unimodal. And that H-star vector actually only has 1s and 2s. So not only do you lose unimodality, but all the peaks disappear. It's just a very flat H-star vector. So I will stop with that and just say we're still working on it, and thanks for having me.